Today I want to talk about something new called binary trees. So I'm going to load up my slides for today. This topic is what we'll cover for most of the next week. It's going to be the focus of our 6th homework assignment. It's a pretty important topic. For what it's worth, a lot of the material from this class is the kind of stuff that they ask you about if you go interview to do an internship, like at Google, Microsoft, Facebook, these kind of companies. They'll ask you, like, during the interview to do a linked list problem or a binary tree problem or a recursion problem. Like, this class is totally interview material, and this topic is definitely one of those kind of topics. So we're going to talk about a structure called trees. This is a data structure, and just if you want a kind of a sneak preview where we're going here, this subject, this tree data structure is what's used to build some of the other Stanford collections that we've used in this class, like sets and maps, as well as lexicon. And it's even related to the priority queues, the heaps that we were learning about last week. So this is an important structure. So with that said, let's get into it. A tree is a directed structure with linked nodes that has no cycles, no loops in it, basically. That picture right there represents something called a binary tree. Binary tree is a structure where every node has 2 pointers to what we call its children. Basically, a binary tree is like a linked list, but instead of just having one next pointer, you have sort of 2 next pointers. And instead of calling them next, we call them your children. And typically what we do is we call them your left child and your right child. And we often draw a tree vertically like this, where you have a start of a tree, which is, in the linked list, the start of the list is called the front, right? But the start of a tree is usually called the root of a tree. There's some cute little, like, tree type of puns here, kind of. We call it the root. You have a pointer to a node that's like the root of the tree, and it has pointers to other nodes, which have pointers to other nodes. Eventually, you get to nulls at the bottom when the tree stops. Okay? And, you can have trees that are not just 2 children. You could have a tree where each node has 3 children or 4 children or 10 children or whatever, but that's not a binary tree. A binary tree is where you have at most 2 children. So if you want to actually be more specific about the definition of a tree, there's sort of what you would call a recursive definition, where you say, well, a tree is either null or it's a node that has data inside and a left subtree and a right subtree inside. And those subtrees could be null, or they could be nodes with data and children inside. And that definition travels all the way down the tree. Anyway, that's a picture of one. And you can implement this in code. We're going to write some code today in C++ to build this thing. And hopefully I can show you how you could use this to do interesting work. Here are some places in general in computer science where trees come up. It depends on the kind of data that you're processing. I mean, we've done some examples that crawl through a directory structure to print all the files and folders. A directory structure could be thought of as a tree where every folder is a parent and all of the files inside and folders inside are its children. It's not really a binary tree because a folder can have many files, but it's a tree. A lot of times when you're writing a compiler, like I don't know if you've ever thought about that, but when you compile your Java program or your C++ program into some sort of executable code, somebody had to write that compiler. And when you're writing a compiler, you have to deal with evaluating expressions. If they say x equals y plus z times w, how do you actually chop that apart and calculate that? A lot of times they make the expressions into trees. The operators of the expressions are parents, and the 2 operands on each side of the operator are the children. So you can model different things in different programs using this idea. There's other examples like, autocomplete often involves trees. Like if you're typing on your phone and it suggests the rest of the word that you've started typing, that's often done by storing words in trees based on starts and ends of words. There's lots of places in trees, in computer science where you see this. I've got a little Socrative decal up here, so I'm going to ask you a quick question. This one's just kind of a quickie one, but I wanted to kind of get one in early. Some lectures I don't get in a question early or at all, so I wanted to make sure I got to one here at the start. So here are some pictures of things that might be thought of as trees. How many of these pictures do you think represent valid binary trees? 1 or 2 of them, 3 or 4 of them, 5 or 6 of them, or 7 or 8 of them? I guess, wait, there's only 7 pictures, right? So I guess D really means like all 7 of them. Take a look and tell me what you think. You can talk to other people if you want to. Okay, a lot of people have voted already, it looks like. Let me pop up the voting results so far. So what do you think? You think that C, 5 or 6 of them are valid trees. So if you voted that, which one or ones, like give me an example of one that isn't a valid binary tree. The one there that has the 3 children? Okay, so that one's not binary tree because it has more than 2 children. What other ones are not valid? I think all the rest of them are. Now, some people maybe eliminate some of the other ones because they're like, well, that doesn't have 2 children and that only has 1 child and so on. But a binary tree, I mean, depends on what you're thinking the picture means, right? That second one on the top row there, it only has 1 child over to the left, but you could think of it as having a right child. It's just the right child is null. So it's still considered to be a valid binary tree. It just only has 1 non-null child. You know what I mean? So that one's still valid. And so are things like this and this. One thing I mentioned on the previous slide is that a binary tree is what we call acyclic. It doesn't have any loops back up to the top. So like if down here the left child went and pointed back up to there, that would break it. That would make this no longer a legal binary tree. Another thing that I think is missing from my definition is there can only be one way to get to a certain node. So like if there were a node here and this one were his right child and his left child, both, that is not a valid binary tree. I feel like there's some sort of Game of Thrones joke about the Lannister kids here or something. I don't know. Never mind. But but anyway, that would also be an invalid tree, right? Okay. So yeah, it sounds like so far so good. Now let's define some terms that we would use when we talk about trees. Each one of the individual circles there is a node, and that's a node in the same sense like when we talked about linked list, right? A node is a little object, a little structure that stores one piece of data and probably pointers to other nodes that have more data, right? And the one at the top is the root, and the ones at the bottom that don't have any children are called leaves. Again, there's lots of like tree terms here from like real life trees. We talk about nodes that are neither the root nor leaves. We call them branch nodes. And you can talk about nodes relative to yourself. The node that's up from you is your parent, and the nodes that are below you are your children, and the nodes that are across from you are your siblings. And typically, because of the way we build the tree, you can only go down the tree. Like if you're here at node number 2, like you have a pointer to it, you can't easily just jump over here to node number 3. Like why would that be? Why can't I just get over here easily from 2? Yeah?
There are no paths leading from 2 to 3. You'd have to start over again at the root.
Yeah, it's kind of like with a linked list. If you're at node number 7 in the linked list and you want to get to node number 5, there isn't really a backwards arrow to go that way. The pointers are one directional, right? And these arrows are meant to be like pointers. This node has a pointer that points to here. And because of that, we can get from number 1 to number 3. But node number 3 doesn't have a node pointer to its parent. The pointers are one directional. So you can go down the tree, but it's hard to go across or up. You're right, that one way to get from 2 to 3 would be to say, well, I can't get there from here, so I'll start over at the root and walk down and find the 3 somehow that way. That would be more likely to work. We also talk about a subtree is a subportion of the tree. Like if I say, here's node number 1, 1's left subtree is all of this. And number 2's left subtree is 4. And number 4's left subtree is null and right subtree is null. So we talk about portions of the tree as being subtrees. Also, we say that a tree has a given height, which is the number of levels tall it is, basically. Sometimes we talk about a node being on a certain level. The root is at level 1. Its children are level 2, and so on, right? Okay. A tree also has a size, just the number of nodes in it. Now, you can make a node class to store data in a tree. And just like we did with linked lists, I think the simplest type of data to start with is int. And so we'll just make a tree node with integers. And it's basically just a little node class. Like I think we had a class called list node in linked list. And it had 2 fields, right? An int data and a list node pointer next. Well, here we just have an int data, tree node pointer left, tree node pointer right. And we can just assign them to point to other various nodes, right? And if we want to code that, we just go to our Qt creator here, and we would make a file called tree node, struct tree node, and we have int data, tree node left, tree node right, pointer left, pointer right. That's all. That's basically all the fields that this thing stores. And then if we wanted to write a piece of code that would interact with it, we could just say like tree node node equals a new tree node. And I could say node data equals, like if I want to make that on the screen right there, maybe node 1 is the top one, so I'll put the 42 in there. So I could just say data is 42. Node left is another node, so let's represent the one with the 59 in it. So node left is the node that has the 59. So I'll say new tree node. And I'll say node left data is 59, bless you. And then node left has no children, so I could say that node left's left and node left's right are null, but the default is that it'll be null, so I don't have to say that. In fact, if you want to compress all this, you can just say that node left is a new tree node that has a 59 as the data. That works because in the node, I wrote a constructor here that takes a data and stores it in the object. So I mean, we could do that. So node left is a new node with a 59. Node right is a new node that has a 27, and then to the right of that is an 86. So a 27, and node right is, was it 86? Is that what it was? I can't remember things for more than half a second. So yeah, OK, there we go. So that's kind of the way that your client program would make nodes. Now, if you remember a week or two ago when I was first starting to talk about linked lists, we did something like this. We made a list node class or structure. And then we made a client main program that created a chain of nodes and like linked them together, right? That was where we started, but really where we wanted to get to was where we had like a linked list class that kind of took care of the nodes for us and did a lot of the operations like adding and removing things and so on. We're kind of going to get to that same place here. So there's a structure for nodes. We already kind of talked about that. What you would really want, though, would be like a class, a binary tree class. And this is like analogous to the linked list class, not the list node class, but the linked list class. The one in the case of the linked list class, what was the field that that class stores, the private variable that it stores? It stores a pointer to the front of the list, right? And that is all it needs in order to implement all of those operations. Because if you say add, you just start at the front and go add it, right? That's the only field that you need. Well, in this case, we're going to write a binary tree class, and the one field that it needs is the root of the tree, the top node. And from there, it can get to all the other nodes and do all the things we might want to do. So we're going to write a class, binary tree, over here, binary tree.h, binary tree.cpp. And binary tree is going to have some various members, and the most important member is the private variable tree node pointer called root. And we're going to use that to implement certain operations on the tree. So one operation is we're going to make a constructor where the main program gives us the pointer to the root, and we'll hold on to the whole tree under that root. The other operations we're going to implement are printing the tree, searching the tree for something, and printing the tree sideways. Those are some operations we're going to write just today. We're going to do more later. Okay? So that's binary tree.h. If we want to write a constructor where the main program can make a tree and pass me the root of the tree, then that's not very hard. So what we'll do is, like back here in the main program, I've made this. And I'm just going to hand all of this to the class, to the binary tree class, just for now. Binary tree class called tree. And I'll construct it, and I'll pass it this node. Now that's going to remember all those nodes. And I wish I could do something like, tree.print. And it would like print out to see out all of the nodes on the screen so we could see them. OK? So, OK, first of all, we want this constructor to work, to make the tree remember all these nodes. So if I go into the binary tree class, here's a constructor where they take a node for the root. And basically what I'll do is maybe I'll call this like initial root, like what they want to be the root. And I'll just say root equals initial root. This object's root variable should be storing the pointer that they gave to me. OK? Now that the class here is storing that, I can write all these methods that will print the tree out, and I can search the tree, and all these different other things.